So let's take a look now at some theorems regarding conservative vector fields. First, a simple definition. A simple curve is a curve that doesn't intersect itself, and a closed curve is one that starts and ends at the same point. Here, this curve here is closed and simple. This curve is simple but not closed. This curve is closed but not simple since it's intersecting itself. And this curve here begins and ends at different points and intersects itself, so it's not closed or simple. We also say that a vector field is independent of path if the line integrals are equal for any curves C1 and C2 that begin and end at the same place. I mean, a way to look at that is if this is A and this is B, and you have some curve here, C1, and you have some other curve here, C2, then the line integral would be equal, okay, since they're beginning at A and B. Any vector field with that property is called independent of path. And we saw that conservative vector fields are the ones that are independent of path, right? And a quick note here that sometimes you'll see integrals, line integrals over closed curves with this extra little circle in there just to emphasize that they're closed, okay? And we have several theorems. I won't go into details in each of them. I spoke about the specifics here. I won't explain each of the hypotheses, but you could read that. F is conservative, right, is equal to the gradient of phi if and only if the curl of F equals 0, of course, with respecting these hypotheses above. That was the test of whether a vector field was conservative. We also have that if a vector field is conservative, then you get path independence. That's the fundamental theorem of calculus, of vector line integrals. And likewise in reverse, okay, we also have this in reverse. You could prove that a vector field is conservative so long as it has the property of path independence. So on top of that, if you also have that your vector field is the line integral over any closed curve is 0, simple closed curve is 0, then you also get that it is conservative. And you could see why that is happening here, because over any closed curve, if your line integral is equal if you go from A to B and equal if you go from A to B through the red route rather than the pink, well, you could imagine going from A to B through the pink route and then returning using the red route, right? And then you would be subtracting whatever you added when you went from A to B. You would then subtract out if you go from B to A. And so you have that your integral of conservative vector field will be 0 over any simple closed curve. Okay? And so in summary, we have this big tapestry of theorems that a vector field is conservative if and only if the curl is 0, of course, on a closed and on a connected and simply connected domain. If and only if you have path independence. That's thanks to the fundamental theorem of vector line integrals. If and only if every line integral over a closed curve equals 0.